Hello, good afternoon, students. Good afternoon, JNV Ramnagar students. So, can you hear me? Am I audible? Am I audible and visible to you? Hello. Yes. Yeah. Okay. Okay. Okay then. Let's continue the class. So, yesterday we were seeing the physical properties and its strengths of the elements, right? So, I have told you that we have four physical property, and out of which we are dealing with the first property. So, that is atomic and ionic radii, right? We are not able to find out the atomic radius of an element because the size of the atom is very small and there is no well-defined boundary for an atom. So we have to find the radius of an atom from the indirect methods, that is from covalent radii, from van der Waals radii and metallic radii, etc. And at last we have seen the ionic radii part. Yeah, here I've told you how to find out the ionic radii also, right? By adding the cationic radius and anionic radius, we will get the d value. Okay. And I have told you the trend also. Across the period, atomic size decreases, and on moving down the group, it increases. And at last, we have discussed the radius for neutral atom, cation, and anion. So among these three, anion will have the highest value, it will have the largest size, and then neutral atom comes, and then cation. Okay, so this concept we have to apply for the same element. Okay, like if I am taking sodium, I have to compare that sodium with sodium plus and sodium minus. Okay, so if the atom is same, then we have to follow this rule, this order. Okay, now for isoelectronic species. So what are isoelectronic species? Atoms or ions which have same number of electrons. Iso means same, electronic means electrons. The species which have same number of electrons, they are called as isoelectronic species. For isoelectronic species, how to find out the radius? So that we are going to see here. So first, I have took a fluorine atom, that is fluoride ion I have took. So fluorine has gained one electron and it has become an anion. So it is F minus. And next I'm going to take sodium plus. Okay, sodium plus and then O2, 2 minus. Now if you see the number of electrons for all these three elements, they remain same because the atomic number of fluorine is 9. Fluorine has gained one electron. So now the total number of electrons in F minus is 10. And the atomic number of sodium is 11. Sodium has lost one electron. So it is minus 1. So now again here also 10. And here the atomic number of oxygen is 8. So it will have 8 electron. And oxygen has gained 2 electrons. So 8 plus 2 is 10. So all the three species, they are having 10 electron. So these three species are called as isoelectronic species. Okay. So all have, but when discussing the radius of these three, you see the size given in the picture on the slide. So all three ions, they are not having the same size, right? So O2 2 minus is having some bigger size, and sodium plus is having the very small size compared to other two, and F minus is having some medium size between sodium plus size and O2 minus size, right? They all have different radii due to the different effective nuclear charge present inside it. Only the number of electrons remains same for all three, but the number of protons is different. The effective nuclear charge which is present inside the nucleus, that is different for all the three species. So the size will also be different. Okay, so now I'll tell you which one will have the largest size value. Yeah, some more examples also I am giving you. It is Mg2 plus and sodium plus. Now what is the atomic number of this magnesium? It is 12. Okay, now magnesium has lost 2 electrons, so 12 minus 2 is going to be 10. And as I've already told you, atomic number of sodium is 11 and sodium has lost 1 electron, so it is going to be 10. Now these two species, magnesium 2 plus and sodium plus, They have same number of electrons, but different effective nuclear charge, different number of protons. Okay, so the size is going to be different. So who is having the largest value, size value? It is sodium plus. Sodium plus is having the largest value. Okay, the effective nuclear charge of magnesium 2 plus is greater than sodium plus. So effective nuclear charge and radius, they are inversely proportional. If the nuclear charge is more for magnesium 2 plus, then the radius of magnesium 2 plus will be very less. Got it? So this is how we have to find out the radius value, and comparing this F minus and O2 minus. O2 minus is having the highest value of radius. Okay, so the repulsion of electron outweighs the nuclear charge here. Okay, fluorine has gained only 1 electron, but oxygen has gained 2 electron. It is having 2 minus charge, right? So it is having 2 minus charge, so it is gaining 2 electron. So the more electron repulsion would be there. So because of that, size of O2 minus is greater than F minus. And ionic radii is inversely proportional to atomic number. So you can use this relation to find out the correct increasing or decreasing order of isoelectronic species. Got it? So I have given few species. So in the last slide, yeah, we had F minus and O2 minus. We are having sodium plus and magnesium 2 plus, right? All are having same number of electron, which is 10. All are having the 10 electron species, right? But the number of proton is different. Okay. So what is atomic number of fluorine? 9. So fluorine will have 9 proton inside the nucleus, and oxygen will have 8 proton. Sodium will have 11 proton. Magnesium will have 12 proton. So now atomic number is inversely proportional to ionic radius. The one which is having the highest atomic number will be smaller in size. Who is that element which is having the highest atomic number? It is 12. Magnesium 2 plus. So magnesium 2 plus is smallest among this 4 species. And then comes sodium, and then fluoride ion, and then oxide ion. Okay, so this is the decreasing order of ionic radii. Got it? So for isoelectronic species, you have to use this relation. Is it clear to JNV Ramnagar students? Yes? This is okay? Yes or no? Yes. Okay. So now let's solve one question based on this concept. Which of the following species largest and the smallest size? So 4 species are given to you. Now can you try for this? Can you try which one will have the largest and the smallest size? 4 species are there. Tell me which one will have the largest size. You don't have to give me the order. Just tell me the species which has the largest size among these 4. Just try for it. I'll give you 15 to 30. Try for it. Aluminium. Okay. Smallest size? Smallest size? Mg? Okay, let's check. Let's see the solution. So what was the trend that we have discussed for atomic radius? So across the period, atomic radius decreases. Okay, atomic radii decreases, and on moving down the group, atomic radii increases. So that was the trend we have studied yesterday. So atomic radii decrease across the period. Now, across the period means first is magnesium comes. I mean, magnesium atomic number is 12. It comes under the S block. And coming to aluminium, whose atomic number is 13, it is there in the P block. So both belongs to the third period, right? Now across the period, size decreases. So when you compare magnesium and aluminium, magnesium will have the highest. Magnesium is the smallest. Al3 plus 3 is the largest. Okay, Hashira, let's check. Let's check. Magnesium, you see here, this is magnesium and this is aluminium. Okay, good. Yeah. So now this is the order. Now we also know that cations are smaller than their parent atom. Yesterday we have discussed a concept, right? I told you that a neutral atom and cation and anion. If I compare these three, anion will have the largest radius, then neutral atom, then cation. Now magnesium is the neutral atom and magnesium 2 plus is a cation, right? Now who is going to have the highest size again? Magnesium. So cations are smaller than their parent atoms. Got it? Now, if you see this magnesium 2 plus and aluminium 3 plus, they both are isoelectronic species, right? Magnesium atomic number is 12, 12 minus 2 is 10, and aluminium atomic number is 13. Aluminium has lost 3 electrons, so number of electrons is now 10. Both of them are isoelectronic. Now, among this isoelectronic species, what we have to do? What relation we have studied for isoelectronic? Ionic radii is inversely proportional to the atomic number. So, who is having the highest atomic number? Aluminium. So, aluminium will have the smallest radii. Aluminium 3 plus will have the smallest radii value compared to magnesium 2 plus. Okay. So, these are the concepts that we are going to apply here. Now, among these isoelectronic, which falls under this relation, according to this relation, Mg2 plus is greater than aluminium 3 plus. So, hence, the given 4 species follows this order, that is magnesium is the largest size element and aluminium 3 plus is the smallest sized element. So the largest is magnesium and the smallest is aluminium 3 plus. Okay. Is this clear for all? If you're having any doubt in this, you can ask me. I'll give you some 10 to 15 seconds. Yes. Okay. Good, Hashira. You have got it. What about the others? What about the others? First, you compare the neutral atom, then compare the isoelectronic species. Okay. Shall we move on to the next physical property? So with this, we are ending up the atomic radius physical property. Yeah, good, good. Thank you, dear students, for your response. Good. So I have told you we have 4 physical property. First physical property has got over. Now let's move on to the second physical property, which is very, very important. Carefully. So ionization, to understand this ionization energy, before moving on to the definition, let me take an atom. Okay. Oh yeah, I have taken the sodium atom. Now this sodium is an isolated gaseous atom. It is an isolated gas. Isolated means it has not formed bond with anyone and it is in the gaseous state. Okay. And as we all know that sodium atomic number is 11. So the 11 electrons you can see in the K shell, 2 electrons are there. In the L shell, 8 electrons are there. And in the M shell, 1 electron is there. Okay. Now, the electron which is there in the M shell, that is outermost electron, is going to get, it is coming out. Okay. Loss of electron takes place from this sodium. So, if that electron comes out, sodium will become sodium plus. Okay. It is becoming sodium plus. Now, if that electron has to come out, it won't come out on its own. I have to give some energy. Okay. The energy required to remove the electron from an isolated gaseous atom in its ground state is called as ionization energy. Okay. Same diameter, then just give me both of the ions are of the same diameter, then which is the most reactive? Virendra. It is Virendra, right? Yeah. I'm not getting your question, my dear. Can you repeat again? You're asking for which part? You're asking doubt from the question that we have discussed now or from this ionization energy? Can you repeat once again? From the previous slide? Okay. Okay. Wait, let me go to that slide. Yeah, let me go to that slide. Just wait for a minute. Yeah. So what is your doubt from this? If both the ions are having the same diameter, means which ions you are asking? Aluminium 3 plus and magnesium 2 plus you are talking about? Those are the only two ions here. I think you are asking, yeah. See, both will not have the same diameter, right? That's what I'm saying. They will not have the same diameter. Their radius is going to be different. If the radius is different, then diameter is also going to be different only, right? Magnesium 2 plus will be smaller, bigger than aluminium. Okay. Yeah, you have got it now. That's great. Good. But let me explain. So this is the radius of both the species. Okay. And this is going to be the diameter. If I calculate, this is the diameter, right? This is the diameter. Radius is different, diameter is also different. No. Radius and diameter, they are directly proportional to each other. Okay. Fine. No issues. We will continue with ionization energy. Yeah, I have took the sodium atom and we have took out one electron from sodium atom. Now Na has become Na plus. The energy required to remove an electron from an isolated gaseous atom in its ground state is called as ionization energy. Okay, I have to give that energy. I am giving the energy from outside to this particular sodium atom. Okay. So it is taking the energy which I am giving. Since I am removing the first electron from the sodium atom, this ionization energy is also called as first ionization enthalpy or first ionization energy. And it is represented by the symbol delta Hi1. Delta H means change in enthalpy. Since it is ionization enthalpy, we are putting I there. And since we are removing the first electron, it is represented by delta Hi1. Okay. And mathematically, this process is represented by like this. Okay. Now this X is the gaseous atom, any isolated gaseous atom. Okay. From this atom, X atom, I am removing one electron and that atom is becoming X plus. Okay. I am giving the energy to the atom and the atom is absorbing the energy which I am giving. So energy is getting absorbed by the atom. Okay. If the energy is getting absorbed, then the process is always endothermic in nature. Okay. If the heat energy is getting absorbed by any system, then we call that process as endothermic process. If the process is endothermic, then the delta H value will always be positive. It is always be positive. So ionization enthalpy are always positive as energy is always required. Means the atom is always requiring the energy and we are giving the energy, it is absorbing that energy. Got it? Any doubt from this? So all these points are very, very important. Ionization energy value will always be positive and the process will always be endothermic in nature since the energy is getting absorbed by the system. Got it? Shall we continue this ionization enthalpy with one more atom? Shall we? If you're having any doubt, just put it in the chat box. Yeah. Now I have took this magnesium. So what is the atomic number of magnesium? Can anyone tell me the atomic number of magnesium? Very easy, right? So first of all, what you guys have to do, memorize all the, very good, Ramnagar students. Very good. Memorize all the, first 30 elements you have to memorize with the symbol. From hydrogen till zinc. Good, Hashira and Virendra. So from hydrogen till zinc, you will have. Okay, so from first 30 elements, you guys have to sit and memorize. Okay, very important. Without knowing the elements, we cannot apply the concepts. Got it? So that's why you have to study. Yeah, the atomic number of magnesium is 12, and the K shell contains 2 electrons, L shell contains 8 electrons, and the M shell contains 2 electrons. Okay. Now I can remove the electron one by one only. So first let me remove this electron. Okay, if this electron is getting out, so we will get Mg plus ion. Since only one electron is coming out, the neutral atom magnesium is becoming Mg plus. And the energy required to remove this first electron is called as first ionization energy, delta Hi1. Okay. Then one more electron is also there. That is this electron. Okay. This electron is here. And if I want to remove this electron, if I remove this, then the configuration will become like this. M shell is absent. Since no electrons are there in M shell now, M shell representation is not given. So now this ion is magnesium 2 plus ion. So the energy associated in the first step is delta H1, and in the second step is delta H2. Okay, delta H2. So this ionization energy is called as second ionization energy. Okay, second ionization energy. So in the magnesium case, less nuclear charge will be there. Okay, and in the Mg plus case, nuclear charge will be more. Since we have removed one electron, magnesium plus will contain only 11 electron but 12 proton. Here 12 electron and 12 proton, and here 11 electron and 11 proton. Okay, proton is nothing but the nuclear charge. Here you see nuclear charge is more. Nuclear charge is more. So because the nuclear charge is more for this magnesium, the energy required to remove the electron from this magnesium plus is more than magnesium. So the second ionization energy is always higher than the first ionization energy, as the removal of electron is more difficult in cation than in the neutral atom. So magnesium plus is the cation and magnesium is the neutral atom. So as we have already studied for size, here the energy required to remove the electron from magnesium plus is going to be greater than the neutral atom. So for this process, for the whole process, that is from magnesium till magnesium 2 plus. If magnesium has to convert to magnesium 2 plus, 2 steps are involved for the removal of 2 electrons. And the energy associated with it is the sum of the ionization energy value. Okay. If you are asked to find out the change in ionization enthalpy value for a given particular atom, what you have to do? Just add the two values and give the answer. You have to get the positive value only, because ionization energy is always positive. Okay. Now let's see the trend of ionization energy. As we have seen for the atomic size, what was the trend for atomic size across the period? Increases or decreases? Across the period, when you go from left to right in the periodic table, will the size increase or decrease? Tell me. Will the size increase across the period or decrease across the period? Yeah, very good. It decrease. No, it will not increase across the period, Ramnagar students. Why you have got confused in this? Across the period decreases. It will reduce. No. You're telling for enthalpy. Yeah, that is correct. But I have asked for size. I have asked for size, atomic radius. Okay. So it decreases and increases on moving down the group. Now let's see the trend for ionization enthalpy. So before moving on to the trend, I'll show you one graph. You can find the answer from the graph. Yeah. So for atomic number versus ionization energy, there is a graph to you on the screen for the elements, for the first 60 elements. For the first 60 elements. So it is starting from hydrogen here, from hydrogen till cesium and beyond that also. Okay, some 3 elements are beyond the cesium. Now, you can see that the peak position, all the peak positions are occupied by, that is, this is the peak, right? Helium, neon, argon, krypton, and xenon. All the peak position, which we can also call as maximas, they are occupied by the noble gases. Means noble gases are having the highest ionization energy value. Why? Why noble gases are having the highest ionization energy value in its group, in its period? Because of the fully filled electronic configuration. Because of the fully filled. Suppose if I am taking neon, what is the atomic number of neon? It is 10. Okay. If I want to distribute these electrons in K, L, M and N shell, first I will put 2 electrons in K shell, then I will put 8 electrons in L shell. Now you see the maximum number of electrons that L shell can accommodate is 8. And 8 is there. So now the shell is fully filled. If the shell is fully filled, then it represents the stable configuration. It is highly stable. So you cannot disturb a person who is highly stable, right? So in the same way, you cannot disturb the all the noble gases which are having the stable configuration. You have to supply more amount of energy to disturb that atom and remove an electron from the noble gases atoms. Got it? So that's why all the maximum position, peak positions, they are occupied by noble gases. And all the minimas, if you see, minimas means the bottom part, they are occupied by lithium, sodium, potassium, rubidium and cesium. Okay, these are the minimas. And they are at the alkali metal. Alkali metals are group 1 elements, right? So noble gases are group 18 element, and alkali metal is a group 1 element. Group 1 elements are occupying the lowest position in that period. Why? Why the energy required to remove the electron from the alkali metals, they are very, very less. You see, they are around 500 kilojoule per mole only. But for noble gases, it is above 2000 for most of the gases. What is the reason for this? It is because of its electronic configuration. All the group 1 elements, if you see, they will have NS1. When I was discussing about the electronic configuration under groups, periods, and blocks topic, I have discussed with you the first group elements configuration, right? It was NS1. NS1. So what these elements can do, they can lose this electron easily. They can lose this 1 electron which is there in its outermost shell easily. So losing the electron is very easy. So because after losing this electron, that system will attain the stable configuration. For this, we can take that sodium as an example. So in the previous slide, we have seen, right? Sodium. When that sodium loses one of its electron, M shell is going off, only L shell is there. L shell is fully filled for sodium plus. So after losing one electron, the system is attaining the stable configuration. That's why that one electron is coming out so easily. So the energy required to remove that electron is very less. So it will have the lowest ionization energy value and it will react very, very fast. It is having the highest reactivity value. Got it? So group 1 elements, they are having the very low ionization enthalpy compared to group 18. So what is the trend observed for ionization energy across the period? Across the period from group 1 to group 18, from left to right, the ionization energy increases. Ionization energy increases. This is the general trend. But there are also factors on which it depends. Okay, ionization energy also depends on the attraction of electron towards the nucleus and the repulsion between the electrons. Attraction of electron. Suppose if this is an atom, this is the nucleus. K shell will have 2 electron, and let me take this as L shell. Okay, L shell will have 8 electrons. 8 or 5 electrons, 7 electrons. It can be anything. Now here, 2 different types of forces will act. One is the force of attraction, and another one is the force of repulsion. Force of attraction will be between the outermost electron and the nucleus. So here force of attraction acts. And there will also be force of repulsion between the electrons, between the inner shell and outer shell electrons, since both are having the same charge, that is negative, force of repulsion will act. So these two forces will act in an atom. Okay. Now, because of this, the effective nuclear charge, which is always less than the actual nuclear charge due to the shielding of inner electron. So, these inner electron, which is there in the K shell or L shell in some of the cases, they will shield the outer valence electron coming towards the nucleus. So, because of this shielding property, the attraction, the force of attraction will become less. Okay, because of that, the effective nuclear charge are also less. Okay, now I'll tell you the shielding effect of orbital. Which orbital electron will shield more effectively? It is S orbital. S orbital electron will shield more effectively than P, then D, and then F. Okay, and shielding is effective when inner shells are completely filled. When inner shells, if this is nucleus and these are the shells, these two are the inner shells, K shell and L shell, right? If K shell contains 2 electrons and L shell has 8 electrons, and if M shell has, let's take 2 electrons. Okay, now L shell and K shell, they are completely filled. If they are completely filled, they will shield more effectively. They will shield more effectively. This outermost electron, it cannot come and get attracted towards the nucleus because the shielding of these K and L shell electron will be more effective. Got it? So the attractive force will be very less. Because of that, effective nuclear charge also becomes less. Now let me tell you the trend across the period. Yeah, I have taken on graph for you, which is there in your book also. So these are the second period element from lithium till neon. So on going from left to right, effective nuclear charge increases because atomic number increases, due to which the nuclear charge also increases. So on going from left to right, charge increases, and because of this, ionization energy also increases. Okay. So the effective nuclear charge is directly proportional to ionization enthalpy. So across the period, ionization enthalpy increases. Okay. Ionization energy is just the opposite of size. So the relation between atomic size and ionization energy, if you see, they are inversely proportional. Across the period, size decreases and ionization energy is increasing. They are inversely proportional to each other. Okay. Just observe this graph very carefully. Gradual increase is not observed. There is some exception between beryllium and boron, nitrogen and oxygen. Okay, just to have a look on it now, I'll explain you the reason within few seconds. Okay, so generally, general trend is across the periods, ionization energy increases. That's all. So any doubt from the topic that we have discussed so far, from the trend and ionization energy? Is everything clear? Yes? Okay. Now we'll, now we'll go with the trend across the group. Trend of ionization energy across the group. So to understand this, I have taken the first group element from lithium to cesium. Lithium, sodium, potassium, rubidium, cesium. On moving down the group, atomic radius increases. Atomic radius increases. So this is lithium, sodium, potassium, rubidium, and cesium. Okay, this is cesium and this is lithium, sodium, potassium, rubidium. Size increases. If the size increases, shielding of valence electron also increases because more number of shells will have will be fully filled. No, so the shielding of valence electron also increases. More number of, if I'm taking cesium, I'll have more number of shells inside this. So all the shells are completely filled. So there is an electron in the outermost shell also. That outermost shell electron will observe more shielding since more number of electrons are present inside that. Okay. So because of this, ionization energy decreases. Ionization energy decreases. So across the period, ionization energy increases, and on moving down the group, ionization energy decreases. Got it? The force of attraction is very less. So if I want to remove electron from lithium, it is highly difficult. I cannot remove the outermost electron from lithium, I have to supply more energy. But if I want to remove the cesium electron, it is very easy. It is very far away from the nucleus, right? So I can remove this easily. I can give very less amount of energy to remove this electron. But here I have to supply more amount of energy because it is very closer to the nucleus. Attraction between that electron and nucleus will be very, very high. So I have to supply more energy and I have to take that electron. Got it? Is this okay? Now we will see the unique nature or some anomalies in trend of ionization energy. That is some exceptions we are going to see. Exceptions. I have told you, right? This beryllium, boron and nitrogen, oxygen in this graph, they are not following the regular trend. Actually, across the period, ionization energy should increase. So lithium is having 520 kilojoule per mole and beryllium is having 899. Boron should be higher than beryllium. But you see, boron is having 801 kilojoule only. In the same way, carbon comes and then nitrogen is having 1400. Oxygen should have higher value than nitrogen, but it is 1300 only. So why there is a decrease? Why there is a decrease for these four elements? Why there is some irregularity? First, I will explain for beryllium and boron, then I will come to nitrogen and oxygen. Okay. When comparing beryllium and boron, beryllium is having the highest ionization energy value compared to boron. Why? It is because of the stable, fully filled electronic configuration of beryllium. Stable, fully filled electronic configuration of beryllium. You see here, this is the valence electronic configuration of beryllium. Beryllium atomic number is 4, boron atomic number is 5. And the electronic configuration of beryllium is 1s2, 2s2, and for boron is 1s2, 2s2, 2p1. Okay. Now second shell is the valence shell for beryllium, which has 2 electron, and these are those 2 electron. Now when you see for boron, second shell is again the valence shell for boron, but in 2s orbital it has 2 electron and 2p orbital it has 1 electron. Let me show you the configuration also. Yeah, this is the configuration. Now the removal of electron from 2p orbital is easy compared to the removal of electron from the s orbital, because I already told you the s electron shielding is more. S electron will be more closer towards the nucleus compared to p. So I can remove the p electron easily compared to s. Okay. So very less amount of energy is required to remove this boron 2p electron when comparing the 2s electron of beryllium. So that's why boron is having the less ionization value compared to beryllium. Got it? Fully filled electronic configuration is the reason. Now, next I will come to, is this clear? Is this clear for all? Beryllium boron story, is that okay? What about the others? Only Virendra is replying. What about the others? I hope all of you are listening. Shall we go? Shall we go with the next thing? All these are very important. Okay, you will get question from the trends. Yeah, the next part is the nitrogen oxygen story. So when we compare nitrogen and oxygen, yeah, good, JNV Ramnagar students, good. Yeah, while comparing these two, nitrogen, oxygen, nitrogen is having the, what is the reason for that? So atomic number of nitrogen is 7 and for oxygen it is 8. For nitrogen is 1s2, 2s2, 2p3, and for oxygen it is 1s2, 2s2, 2p4, right? So now this is the valence shell and this is the electronic for nitrogen, 2s2, 2p3, and for oxygen, second shell is again the valence shell which has 12 electrons. Now here you see nitrogen is having the half-filled configuration. Nitrogen is having the half-filled. All the 3 p orbitals are having 1 electron each. Is called as half-filled configuration. Whereas the oxygen configuration is called as partially. This is partially filled. Oxygen is partial. It is neither half filled nor fully filled. If you find any configuration in between these two, then you have to call that as partially filled configuration. Okay. Now oxygen is partially filled, nitrogen is half filled. Half filled configurations are more stable. Half filled configurations are more stable compared to partially filled configuration. Okay. So I already told you the more stable system, okay, needs higher amount of energy to bring that electron out. So the nitrogen requires the higher amount of energy for the removal of its valence electron. Nitrogen is having the extra stable half-filled configuration, and here repulsion between electron and electron arises here, due to which the ionization energy of nitrogen is more compared to, okay. So beryllium boron, in that case, you have to keep in mind the fully filled configurations are more stable. That's why beryllium had highest value. And here, half-filled configuration. If I compare all the three, which one will be more stable? Now I'm comparing fully filled or completely filled configuration, completely filled and partially filled and half filled. Which one will have the highest, which one will require highest ionization energy value? You tell me when you compare these three. Any idea for anyone? Completely filled, half full as well. Both will have the same value. Both will require same amount of energy to remove the electron. Both half filled and fully filled. Virendra. Completely filled configurations are more stable. Then comes half filled, then comes partially filled. Okay. So the energy required to remove the electron from the completely filled configuration is more stable. And then comes these two. So now with this concept, okay, with this anomalies, we will try to solve one question. Yeah. Among the second period elements, the actual ionization enthalpies are in this order. They are following this order. Explain why nitrogen has higher ionization energy than oxygen. So what is the order of this second period elements actually? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So this is the order which is there in the periodic table, right? So across the period, ionization energy should increase. So it should have followed this order only. Neon should have the highest value, then comes the remaining element. But there is an exception arising between these two elements and the nitrogen and oxygen. So this is the order observed. This is the order observed. So we know the reason. Just now I have taught you, right? Now we know the reason. Now you tell me why nitrogen is having the highest ionization energy value than oxygen. In a single word, can anyone explain me the answer for this? Nitrogen is half. Very good. So boron is having 2s orbital. Electron has to get removed. That, yeah, good. And oxygen is having, it is not oxygen, it is boron. Okay, sorry. This is beryllium and this is boron. Yeah, 2s electron is more strongly attracted towards the nucleus than 2p electron. More energy is required to remove the electron. So beryllium is having the highest ionization energy value. Now when you compare nitrogen and oxygen, nitrogen is half full. That's why. Now let's move on to the third physical property, that is electron gain enthalpy. What is the time now? It is 3:52. So if I start this, yeah, shall I start or shall I continue this in the next class? What do you guys say? You are giving thumbs up for my which question? Shall I stop? No, ma'am. You don't want me to continue? Okay. Start, ma'am. Okay, even if I start now, I will not be able to complete this property, right? And also, today is the last day of this year, which I'm seeing you all. So I'll continue this in the next year, okay? In the next class, I will continue this. So I'll stop here. So far we have completed, yeah. So far we have completed atomic size property and ionization energy property. Study, study, study. Don't waste your time. Sit and study and solve n number of questions as much as you can. So we will all meet up in the next class, that is next year. Okay. Thank you so much. Advance Happy New Year to all of you. Thank you, students. Thank you so much. Take care. Jane, thank you, dear. Thank you.